Good morning, good afternoon, good evening, wherever you're watching us. This is SDC 2020, and today we're going to present a paper which tell you why do customers require media path redundancy in a storage array environment where simple latency hardware passes are required. The hardware is not required, but it's going to be replaced by a software entity. My name is MK Jibi. I'm a technical director from NetApp ESG. My co-author is Mr. Joey Parnell. He's a software architect for NetApp ESG. So the current problem today, we have several emerging white box storage system, which replaced mature and robust drive network with simple point-to-point, such that those point-to-point, all the ports on the drives has only a single port. Now, in this presentation, we're going to share with you how the storage product has a dedicated port to drive, and there is no hardware path to another port that establishes the redundancy. And the redundancy access of this method to the media is provided via a network called non-transparent bridging or Ethernet or other networks to overcome lack of redundancy in the topology. The current problem today, a commodity of white box storage with less custom hardware become prevalent. Some parts of the hardware designs that provide fault tolerance relied mainly on the high availability provided by the hardware platform, and such platform are no longer present. Today, the hardware designs are enabled via a software-defined storage products, which have lower hardware cost and complexity. And so, in addition, we have the I/O access is expected to increase and have very low latency and no impact to performance. Just such criteria motivate the use of point-to-point peripheral component interconnect, especially for PCI, for NVMe connections in these hardware designs. However, such implementation sacrifices the redundancy provided by more robust storage networks like cross-connection packet or fabric, which is in the past media to the storage system. In a storage system, lack of redundancy in a storage hardware to physical media like HDD and SSD introduces a single point of failure, which is not acceptable to enterprise storage customers. So the goal of this paper is to provide the user with an I/O policy management so that it will reduce or eliminate any non-optimal access, okay, over the period of time of using the storage product, in such a way it will provide fault tolerance, it will minimize disruption, which is caused by fault, and also provide an automatic drive recovery mechanism for like misbehaving drives. So if you look at this graph, on the graph on the left, figure 1, show you the old technology where you have each drive has dual channels on each port, and the storage controller A has 2 passes to this drive, and storage B has the other alternate passes. So in case there is a failure from the red pass fail, then A will be able to access the same drive via the green path. That is where this drive such channels will add cost to the drive, and this is what the method of this paper is going to do. So if you look on the right-hand side, you'll see that all the drives has single port, and each port has one channel. And so A can have access to one port on drive X. Same thing that B has one access to drive X. If the red pass fails to the green pass, what storage A will do, it'll go through this internal network so that B can access that drive via the green path. By using what? By using a software implementation that provides such redundancy where it routes the IOs over that internal network. Okay. So the solution that we are describing in this paper, that the fault tolerance is provided by the storage controller that has only dedicated one port, and there's no other alternate hardware path to that drive. The redundancy access is provided via the network between controller A and controller B, as I showed you in the previous figure, and via the NTB, or the non-transparent bridging, or any other network so that it will provide that redundancy through that network. And also it provide a non-optimal path, okay, non-optimal IO path to physical media. What it does, introduce a new problem, a new potential, a new impact to the host applications. Any asymmetric access or non-optimal access could impact the host application in a negative way. This problem is mitigated by not eliminated, but mitigated but not eliminated by the storage controller caching. So what are the methods that we're going to present to you today? In this solution, we're going to show you that how the controller firmware implement this IO policy management that allow you to reduce and eliminate any non-optimal IO access over time. The redundant controller will implement different modules to solve the problem, the latency problem, and the redundancy. By doing what? By using those one of these four methods. One is IO shipping module to execute IO operation. Another is a multipathing module to select the path to media. A third one is IO policy management module to eliminate the usage of non-optimal passes. And finally is a serviceability module that aid the user by providing notification and action to take for these features. And now I'm gonna pass the presentation to Mr. Joey Parnell to go over figure 3 and 4 to illustrate how these path and function modules are designed and function and working. Joey?
Yeah. So this is actually the same diagram that Dr. Jibby showed before, but I wanted to kind of delve into it a little bit. So as was shown before, if the path from storage controller A to port 1 on drive X fails in a network environment in figure 3, then it will switch to the other local path, still going through the same storage controller. Whereas now in a point-to-point network or a point-to-point design, you have to go through the internal network to process those IO operations. And what that means is you have to suffer the latency of going over that internal network to complete that IO. And that latency presents a class of problems that we will have to solve with those other modules that Dr. Jibby mentioned, such as a module that's going to select the best path to use at any given point in time, a module that's going to, over time, reduce or eliminate the reliance on using that non-optimal path, and then a module that also alerts the user and gives the user control over how to address the issues that occur. Go ahead to the next slide. So the IO shipping module, this is the, I guess, the bread and butter of the operation, where you have to be able to make sure that any IO that you write to the drive can be serviced through either path. So we need a module that is able to write that data over the internal network, just as we can do this in software to avoid the problems that come with lacking redundancy. So one thing to mention here is this isn't actually a required feature because you might ask, why do we even need this? Why don't we just fail the drive and reconstruct to another parity drive and recover that way? Well, what we've seen through analyzing telemetry data with our E-Series products is that in 0.3% of our storage systems deployed, at least one drive has a failed drive port. So that's a significant amount of systems that would have to be undertaking reconstruction, which can take hours or days depending on the size of your configuration, the type of media, and so on. So this is absolutely a required feature to be able to ship this, to be able to issue this I/O through another path, even if you don't have a physical path. So I'll come back down into the weeds a little bit here. So this I/O shipping module needs to be able to efficiently process this I/O using the internal network, and one way of doing so is separating the messaging and the data transfers into different transports. For example, you can send the messages over an internal network, Ethernet, and then you can mirror the data using non-transparent bridging. So non-transparent bridging is basically just a PCIe chip that connects memory from multiple controllers into the same PCIe fabric so that we can mirror data into memory addresses across that link. And one thing we can do is dedicate a cache mirroring region on each of the storage controllers, and then that way we can just send messages over a slower transport, and then send over a slower transport such as Ethernet or TCP that has acknowledgments, and then send the data over NTB, which is a very efficient way to mirror data into known cache addresses. Like any architecture, this can go wrong, and if it goes wrong, there will be an error. And errors, the way we handle them, depend on where the error. It depends on the communications between the two controllers. So if the two controllers are talking to one another just fine, then those errors can be propagated, and then the multipathing module can react to that error, whether it means to select another path or to escalate to another module to take recovery actions. So as long as they're talking, they can propagate errors and make smart decisions. If the storage controllers do not have interconnectivity, like they just stop talking to each other completely for maybe a hardware fault in the Ethernet chip or whatever, then the originating storage controller will just time out the I/O. Go ahead. So the multipathing module, this is kind of the brains behind the redundancy, the path redundancy. What it does is it selects the optimal path to media, and it does that by listening to drive events. And those drive events can be emitted either during the storage controller's start of day process, that can occur when drives are inserted or removed, and they can occur when drive ports transition between states, for example. But one thing that's one particularly challenging aspect of this is that drive events are asynchronous and sometimes process slower than you would hope, depending on the type of media. So it requires quite a bit of smarts in the processing code to make sure that that events are debounced properly. That if you have a quick push combination, that you don't process things in the wrong order, and things like that. Flaky drives are also a problem because flaky drives can emit events much more frequently than you would think, and go online and offline in kind of a sequence. So this multipathing module has to be able to handle all of these things in order to select the optimal path in the given circumstances. So these, whenever the drive events are handled and these accessibility changes are processed by one storage controller, that storage controller also needs to notify the alternate storage controller of its understanding of the path states, so that they can agree on their view of the world, so they can make smart decisions together. And they do that by communicating together through the internal network. The multipathing module, it maintains a collection of paths, and it also maintains an indication of the expected latency of each path, so that paths can be denoted as optimal or non-optimal, and you can have different grades within there depending on the latency. Go ahead. So the multipathing module, it selects the path, as I think I already mentioned, to what path should be used for given I/O as I/Os are coming in. And it's not happening in the I/O context. The I/O context is just going to whatever the active path is, and then the configuration context is switching the path based on these events. And the optimal path is selected in normal conditions, but when a port failure is observed, that's when things get pretty interesting. So a non-optimal path will be selected based on the expected I/O access characteristics, and typically latency is the important one. And the I/O shipping module will then perform that I/O operation, as I already detailed. The I/O timeout and the I/O retry count, these are things that in a storage product may actually be more fixed or hard-coded, but this asymmetry will require you to rethink that. So if you're going over a much slower route with your I/O, you need to rethink what your I/O timeout should be, because you may breach that timeout on when everything is optimal actually, and it's just kind of backing up because it's a longer latency. You also probably want to decrease your I/O retry count, because you don't, if in an optimal case you would retry an I/O 5 times with a 100 millisecond timeout, you wouldn't want to retry 5 times with a 1 second timeout, because you're increasing the overall timeout time back to the application. So the timeout and retry count need to be tuned. You probably want those two combined to take as long as it would have taken before on an optimal case. So for example, if you were doing 5 for 100 milliseconds, you might want to do 2 for 250 milliseconds or something like that. And any error, sorry, what was the last? I think I had one more point. Oh yeah, so each retry is actually reevaluated by the path selection algorithm. So a retry might actually occur on a different path depending on what you're observing with the access characteristics. Okay. So the I/O policy management module, this is the purpose of this module is to make sure that your non-optimal accesses are minimized to the extent possible. And this is going to require talking about asymmetric characteristics quite a bit. So redundant storage controllers may be symmetric or asymmetric, depending on their hardware design. E-series is an asymmetric design, meaning if your I/O goes through one path, it may be faster than an I/O or significantly faster than an I/O that goes through another path. And what we do, the reason why that's true is we have volume cache that is owned by one of the controllers. So only one controller is the owner of that cache, and then that's what we call the volume owner. And so we'll use this concept of volume ownership to maximize our performance on the optimal path, and then we'll use the concept of transferring volume ownership to manage around and avoid the shipping as much as possible. So the storage controller can initiate volume ownership transfers. So for example, if you have a volume that is owned by the A controller, but the port for one of the drives that is underlying that volume is failed to the A controller, the best thing to do is actually to move it to move that volume ownership cache to the B controller, so that now all the IOs are being processed in an optimal fashion. Then in the background we can remediate things. So the storage controller, what we do is we maintain a mapping of physical media to logical blocks, and this is kind of like a reverse mapping from the RAID group to the disks. And what we can do with this is, use our understanding of the volume configuration and the drive distribution to eliminate, to the extent possible, the amount of IOs that are going over this non-optimal path. And it actually can get quite complicated. For example, if you have a RAID group that has one drive with a failed path to A and another drive with a failed path to B, in that case, you can't actually, if that volume is across both of those drives, there's nothing you can do to avoid shipping. But in the typical case, you just probably have one drive with this problem, and we can avoid the issue altogether. But using this mapping, we can identify the volumes that we need to transfer and transfer them to the optimal controller. Okay, go ahead. This is an eye chart here, but there's a lot to unpack here. So there's a concept in in any asymmetric storage controller system that you have volume transfers, and you want to, some of these volume transfers must occur. Other volume transfers are kind of optional. So what we want to do is, when any drive port fails, we want to immediately disallow any other features from transferring volumes that are kind of optional. It might be like, oh, it's nice to do this. For example, automatic load balancing will redistribute volume ownership proactively. Well, we don't want to do that because an event has occurred that takes precedence over kind of those background operations. So that's the first thing we do. Then what we'll do is initiate drive power cycle operations. What we want to do is reduce the disruption as much as possible. So we actually have an escalating drive power cycle state machine, and what it does is it starts by power cycling just one port, the failed port, and then we kind of escalate to failing the drive, and then not failing. This is power cycling. So we power cycle the port. If that doesn't work, we power cycle the drive. And what this is trying to do is kind of just kick the drive into becoming back optimal, and that happens way more often than you might expect. That actually fixes the issue or addresses the issue. So what we do when we do that power cycle is we have a mechanism to avoid power cycling too many of the drives at once. So back to that example of a bunch of drives in the same RAID group, we don't want to power cycle multiple drives in the same RAID group at the same time, because that's a big data integrity risk. So we have kind of limits for, if it's a RAID 6, this is how many you can. If you have RAID 5, this is how many. And basically avoiding dragging out the power cycling so that it takes too long of a time, but we also don't want to risk data integrity by power cycling too many at once. So that's the first thing we'll do. And then what that drive power cycle does is it might initiate a rapid reconstruction of the data, and that depends on the RAID level. What it does is we can treat the IOs to those segments as degraded, and we'll do some interrupted write logging to an intent log, and then we'll do a reconstruction on the critical stripes first. And what we'll do there is basically we're just minimizing the amount of time that it takes to power cycle this drive, because it could be done very quickly. Next, what we'll do, we'll wait a little bit after we try to do that. Did that solve the issue? If not, we need to go further. So the next step is to initiate drive failures. And what this will do is this will fail the drive so that the data, in your RAID group, you'll need to use your parity to reconstruct. You'll need to use a hot spare, or if it's a disk pool, you'll need to use reserved capacity. and it'll just start writing to other optimal drives that have redundant paths. We want to avoid this, this obviously failure is what we're trying to avoid because that's what the whole IO shipping is about. But if nothing is reviving the drive, then you have to do something. So that's our action. And then finally, what we can do is initiate drive evacuation. So if a drive failed, we can migrate data to spare capacity on a hot spare or disk pool space, as I mentioned. This is an optional feature because a user might not want it to do that. And another thing, so this entire feature, all the way back up to step up a level, this entire feature is optional. You can disable this feature. For example, if you want it to just fail the drive right away as soon as a drive port fails, you can set it to do that. But this just depends on the customer and their use case and what they want to occur. Okay. Okay, so serviceability, this is important because this is what allows us to report conditions to the user and let them make a decision. So, we report the drive port failure to the customer in our management interface. We call it our recovery guru that lets them know, hey, here's what happened, and here are the things that you can do to remediate the issue, and contact support, things like that. But we can do is, what we will do automatically is go ahead and turn off or turn on the drive fault LED to indicate, when the customer goes back into the lab or, system engineer goes back into the lab, they can see, oh, this is the one that's got the issue, indicate the problem. And then when the issue's resolved later, we'll turn off that LED. Also, this is kind of a critical distinction that needs to be understood. We have to turn off the controller fault LED when this occurs, because when a drive port fails in a point-to-point design like we're talking about here, if your port to the A controller has failed and you are processing your IOs through the internal network to the B controller, if the B controller needs to be serviced, that is your only accessible path to your media for this drive. So we can't allow you to service the B controller if your port on one of your drives to the A controller has failed and you have active IO going on. You can't service that alternate controller. So what we have to do is disable that LED so that the customer knows you cannot pull this controller right now. This is you are lacking redundancy. You're limping along. Do not take any actions right now. So what we'll do, we take other actions as well, which I'll go into here. So we implement an isolation diagnostic method. What this does is it lets us check to see how many drives have failed a port to this controller. If it's one drive, then it's probably a problem with the drive. Maybe the drive needs to be replaced if none of the recovery actions succeeded. If it's 8 drives that have a failed A port, then it's probably not the drives that have the fault. It's probably the controller. Maybe you have hardware issue, bent pens or something. So so in that case, we're able to tell, is it the drive ports that are the problem, or is it the controller? And we can alert the customer to take the correct action depending on which one it is, based on a threshold of how many drives. So we can protect the system configuration that way. We also disallow kind of just routine maintenance during this time. If a drive port has failed, we don't want you doing firmware updates, either controller firmware or drive firmware updates, because we stagger reboots when we do those upgrades based on certain things, and we don't want a staggered reboot will actually cause you to lose access if you only have access through one controller. Another thing we do is we migrate internal metadata. So, a lot of our storage features require internal metadata to be stored on a dedicated region of the drives. And, that internal metadata might be critical for some features. we don't want that internal metadata to be on a drive that is not redundant. So we move that data to a redundant drive in the background when this occurs. A couple other things I want to mention here. These actually aren't specific to serviceability. These are just generic things, but this is what we talked about here is one potential implementation. There are others that have been explored that we kind of pursued the route and then decided to implement it the way that we did. And I did want to just mention those in case it causes anyone to trigger a thought in anybody's mind. And I'm happy to go into that further. But another way to achieve the same thing would be to use NVMe over fabrics to provide this redundancy, to basically use the storage controller as an initiator and a target in an NVMe over fabrics kind of topology. What we explored to that extent was that this would result in higher latency than what we implemented. What we implemented was a ultra low latency data mirroring phase and a higher latency messaging phase that goes over Ethernet. But that's not to say that this is not a feasible thing, and in fact, it may be very feasible. Another approach that you could do that we explored a little bit was extend the addressable memory map between the redundant storage controllers and have basically put your NVMe submission and completion queues in that addressable memory map that you can access between the two controllers. So you could do this through NTB as well, but what you could do is use NVMe submission and completion semantics instead of a roll your own messaging scheme, and that is certainly a feasible thing as well. Go ahead. Dr. Gibby, you want to take it from here?
Yes, thank you, Joey. So Joey went through the detail about each one of these mechanisms. You'll see that the solution for the point-to-point connection in establishing redundancy through this method, you'll see that the redundancy of the drive network topology, especially the mature one with an inexpensive white box hardware. You see that what Joey described, we solved the problem by providing latency in software instead of hardware. Such as what we did, we redistribute the workload so that we can minimize any performance impact or penalty. We were able to recover from misbehaving drive in an automatic fashion. We were able to recover optimal configuration, restore that configuration for a customer workload, and also we notify customers about any faulty component that occur during that mechanism. So what is the takeaway for our audience today? We can tell them that that the storage area network customers, especially at the product level, different product level, that they expect much higher enterprise quality today, with the expectation of continue to have low cost. And the low cost, which is basically driven by saying that the hardware is cheaper, the software is free, almost free. We need a product that meet that enterprise quality. And also, the takeaway also, you can look at these enterprise features that are lacking from converged hardware. Also, we need to provide robustness of drive network topology, especially in a white box server hardware, without impacting the performance, without losing the redundancy, while maintaining low cost with an enterprise quality. Okay, so this method that Joey described in details did show you that the drive path redundancy was preserved, and it was preserved by software, by establishing the redundancy through the NTB network or Ethernet. And that network comes with certain problem, but the method that we described in this paper did solve the problem and identify a fault to the user when need to be identified. And did that by redistributing the network workload among drive via an asymmetric logical volume, like we discussed. The E-series is asymmetric, and we were able to recover in a very automatic way, recovering from drive that are misbehaving, drive that come up and then go down and then come back again, stuff like this. We were able, and the concept of power cycling the drive and give the drive another chance to come back. And if not, then we shoot the drive, or we can evacuate it depending on what the customer needs. With that, thank you for listening to our presentation. And please, if you have a questions, please email us the question or send them to the SDC conference, and we'll be happy to answer any question you have and provide it in a very timely manner. Thank you, and have a good day.